In section 1.2, we're going to review everything we've seen about radical expressions and radical equations from our previous algebra experiences. First, a quick review of exactly what radicals are. Radicals. If some number to some exponent gives us some answer, then we say the nth root of that answer is the previous base. And an important subnote here is that we can only take even roots of non-negative numbers. We can take odd roots of anything, but even roots only with non-negative numbers. So for example, if we had the square root of 25, one might think of the square root of 25 as the square root of 5 squared. And because exponents and radicals are inverses of each other, we're just left with the base on the inside. So the solution becomes just 5. Similarly, we can do a higher root, maybe a cube root of 64. And what we're looking for there with the cube root is something to the 4th power is equal to 64. I'm sorry, not the 4th power, it's a third root. We're looking for something to the 3rd power to equal 64. And you might recall that 4 to the 3rd power equals 64, so the 3rd root then must be that base of 4. Similarly, if we wanted the 4th root of something like 81, what we're looking for is the 4th root of 81, which is something to the 4th power. Well, 81 is 3 to the 4th power, so the 4th root then is just the base of 3. Now, a quick note about negatives. We already said that we have to be careful with negatives. If the index is odd, like the 3rd root of -8, there really is no concern with the problem, because we can have a negative number as a base, -2 to the 3rd power, under a 3rd root. The answer is just a negative number, a -2. However, if the index is even, say we're just taking the square root of -9, we have no way to write this as the square root of something squared. Because whenever we square it, we'll always end up with a positive number. We'll never end up with that -9. So when the index is even and the radicand is negative, we say that it is not, well, we could say undefined, but I'm going to say non-real answer for now. We'll talk about non-real numbers in another video, but for now we'll just say we can't have a negative under a radical. Now these radicals were all nice because they simplified really quickly to the numbers we needed. However, simplifying radicals usually involves a little bit more. Sometimes we can't pull everything out of the radical like we had hoped. And so what we're going to do is we're going to consider the prime factorization of a number and then we can divide exponents by the index of the radical. So for example, if we wanted to take the square root of 50, several ways you can find the prime factorization. One way is to say 50 is 2 times 25, and 25 is 5 times 5. So the square root of 50 is going to be 2 times 5 squared. With square root, we know the index is 2, and so we can divide the 5 squared, divide that exponent by 2, and we get a single 5 coming out of the radical. The 2, there's no exponent on it. With no exponent, it's going to stay inside the radical. And so we will say the simplified form of the square root of 50 is 5 times the square root of 2. Similarly, if we've got the cube root of 16, we can factor 16 to 4 times 4, and 4 to 2 times 2, all the way down to prime numbers. So we say the cube root of 16 is the cube root of 2 to the the fourth power. Now, when we take that exponent of 4 and divide by the index, we get a 1 with a remainder of 1. That 1 tells us a single 2 is going to move out, and the remainder of 1 tells us a single 2 remains inside the radical. Keep the index on the problem, and we have 2 times the cube root of 2. And we can extend this idea out into longer problems. Say we've got the fifth root of 64, a to the fifth, b to the eighth, c to the 12th. Well, first, the 64 needs to be factored. 64 is 8 times 8, and 8 is 4 times 2, and 4 is 2 times 2. And so we'll see that factoring out. 64 has 1, 2, 3, 4, 5, 6 2's in it. So we'll say that's the fifth root of 2 to the fifth, a to the fifth, b to the eighth, c to the 12th. Now we can divide all of these exponents by the index. Oops, did I say 2 to the 5th? There's 6 of them, right? Should be 2 to the 6th. There we go. So now when we divide these exponents by the indexes, whatever is our whole answer comes outside of the radical, outside of the fifth root, and whatever remainders we have will remain inside the radical. So 2 to the 6, 6 divided by 5 is 1, remainder 1. So 1, 2 comes out, and 1, 2 remains. A to the 5th, 5 divided by 5 is 1, remainder 0. So 1a comes out, and no a's remain. B to the 8th, 8 divided by 5 is 1, remainder 3. So 1b comes out, and 3 remain inside the radical. For the c, 12 divided by 5 is 2, remainder 2. So 2 come out, and 2 remain inside the radical. We have our simplified solution of 2abc squared times the fifth root of 2b cubed c. We can even play with this in multiplication. Say we've got the square root of 5a squared b cubed, and we multiply by the square root of 15ab to the 5th. When we combine these together, we'll want to make sure the numbers are factored. The 15 is 3 times 5, and the 5 is already 5. So under a single radical, we've got a 3 and a 5 squared. We've got a total of 4 a's and a total of 8 b's using our exponent properties from section 1.1. And now we look to see what we can pull out of the radical. The 3 remains behind because there's no exponent on it, but 5 squared means a single 5 can come out when we divide by the index of 2. A to the 4th, boy, I really can't add today. 2 plus 1 is 3. That should be a to the 3rd. A to the 3rd. So we have 3 divided by 2 is 1, remainder 1. So 1 comes out, and 1 remains behind. On the b to the 8th, 8 divided by 2 is 4, remainder 0. So we have b to the 4th, and 0 remaining inside the radical. So when we're multiplying radicals, it's really nice because we can just combine the inside stuff. Dividing radicals gets a little bit more involved. First, I'm going to kind of introduce them with this simple problem. How about the square root? Let's do a cube root, a little more interesting, of 5 over 27. The way we take a radical of a fraction is we take the radical of both the numerator and the denominator. So we would have the third root of 5 over the third root of 27. Well, actually, I probably should have factored that 27 first. 5's already prime. And the 27 is 3 times 9 and 3 times 3, so we have 3 cubed. Cube root of 5 on top, in the numerator we can't do anything with it, but the cube root of 3 cubed, when we divide the exponent by the index, a single 3 comes out, and there's nothing left behind. So we have the cube root of 5 over 3. And this problem worked out all right because in our final answer there's no radicals in the denominator. In mathematics, we don't like to see radicals in our final denominator after we simplify them, which means on occasion we might have to do a little bit of work with this thing called rationalizing the denominator. Basically, we're saying we have this rule of no radicals in the denominator. The way we do this is we are going to multiply by any missing factors. On top and bottom, numerator and denominator, because we have to stay balanced. Here's what I mean by that. If we've got 3 over the 5th root of a squared, we don't like that 5th root in the denominator. So what we're going to do is we're going to multiply by a 5th root in both the numerator and denominator that has all the missing factors to get rid of the 5th root in the denominator. Notice our factor is a squared. We already have 2 a's, but we have a 5th root. To get rid of that 5th root, we need a total of 5 things. 5 a's. We already have 2 of them, so we need 3 more of these a's in both the numerator and denominator. When we do that, we've got a 3 outside the radical and a 5th root of a cubed in the numerator. Let's do that in a different color. 3 times the 5th root of a cubed. And then in the denominator, we've got 5 things under a 5th root, which means a single thing comes out, a single a. And for our final rationalized solution, we have 3 times the 5th root of a over a. Let's try another one. How about we do the 6th root of x cubed over y squared? Again, with fractions, we need to take the radical of both the top and the bottom, the numerator and the denominator. So we will do the 6th root of x cubed over the 6th root of y squared. Then we'll say for 6th root, how many more things do we need to clear the denominator? Well, right now it's y squared, so we need 4 more y's, y to the 4th, in both numerator and denominator. And because these are all under the radical, we can go ahead and multiply them together, x cubed y to the 4th. All over, we've got 6 things under a 6th root, a single y comes out, and we have our final solution. A square root problem becomes almost a simplified version of this, maybe the square root of 3/2. First, we need to take the radical of both the numerator and the denominator, root 3 over root 2. And with square roots, the index is 2. We've already got a single 2. We need a second 2. So we'll do square root of 2, numerator and denominator, to give us the square root of 6 over 2. So we've talked about how we can multiply and divide with radicals. Multiply, we can just combine the stuff. Divide, we want to make sure we take the radical of top and bottom if needed, and there's no radicals in the final solution. But what about how we add or subtract with radicals? Well, this is basically going through the exercise of combining like terms, or in this case we're going to call them like radicals. Just like if I had 5x plus 2x, we would pretty quickly say that was 7x by combining like terms. We can consider 5 times the square root of 3 plus 2 times the square root of 3. They both have a square root of 3 on them, which means we add the numbers in front 7, and we still have the square root of 3. Notice the radical part acts like a variable. And if it's a like term, we can combine it. So if we've got 8 times the 4th root of 5x plus 2 times the 4th root of 5x minus 7 times the 3rd root of 5x. We look for like terms in order to combine them. Well, you'll notice the 4th root of 5x is a like terms, but not the cube root. Cube root of 5x is close, but close only matters in horseshoes, scud missiles, and slow dancing, not in math. So as a result, we can only combine the like terms of 8 plus 2 to get 10 times the 4th root of 5x. And we still have negative 7 times the cube root of 5x. Combining a lot of these concepts together, we're now ready to simplify an expression such as the square root of 125 plus 17 times the square root of 1 over 5 minus 5/4, we'll make that to the negative 1/2 power, plus the 4th root of 25 over 16. There's a lot of pieces to this problem, and each piece simplifies differently. The 125 we can simplify by factoring it out to 25 times 5, and 25 is 5 times 5. So really the 125 is the square root of 5 cubed. And if we divide the exponent by the index, a 5 comes out, and left under the square root is a 5. The second term, 17 times the square root of 1/5, is taking the square root of the top and bottom is 17 square root of 1 over the square root of 5. And we know we can rationalize the denominator by multiplying by the square root of 5 in top and bottom. This will give us 17 square root of 5 over the denominator of 5. The third term is 5/4 to the negative 1/2. We can use our exponent properties that we know that flips the fraction over 4/5. Keep the negative. Well, we'll bring the negative down. So we got a plus between and then a negative. The 1/2 power means we are taking a square root of both parts. Well, the square root of 4 is 2 over the square root of 5. And then we can rationalize the denominator by multiplying by the square root of 5. So we have 2 square roots of 5 over 5. Finally, the 4th root of 25 over 16 becomes an interesting challenge. 25, when we factor it, is 5 times 5, 5 squared. 16, when we factor it, is 4 times 4, 2 times 2. So we have 5 squared over 2 to the 4th, and we want the 4th root of that. Well, when we take the fourth root of top and bottom, we have the fourth root of 5 squared over the fourth root of 2 to the fourth. Which is nice because, in the denominator at least, the fourth root of 2 to the fourth is clearly 2. But what about the fourth root of 5 squared? If we recall, we can write that index as an exponent. That's going to be 5 to the 2/4 power, where the index is the denominator, and we can reduce 2/4 to 1/2, or simply the square root of 5. Each term in this problem has a like term of the square root of 5. So as we start to combine things, 17 minus 2 is going to be 15 root 5 over 5, and that's going to reduce to 3 root 5. So we have 5 root 5 plus 3 root 5 plus root 5 over 2. 5 plus 3 is 8 root 5 plus root 5 over 2. Common denominator, so we can add them, is 16 root 5 over 2 plus root 5 over 2 gives us a final answer of 17 root 5 over 2. That is how we can add and subtract with radicals. Simplify each term and then combine like terms. One last thing to talk about then with radicals is how we can actually solve radical equations. It's basically going to be a two-step process to take care of radicals. We need to get a radical alone, and then we can clear it with the opposite of a radical, which is an exponent. A reminder from our previous days in algebra is that we need to check answers in even radicals, because sometimes the answers won't work. So starting really simple, if we have the square root of 2x minus 3 equals 5, the way we solve this, the radical, you'll notice, is alone, is the opposite of a square root is a second power. We will square both sides so that second power and second root undo each other, leaving behind 2x minus 3 equals 5 squared, or 25. Add 3 to both sides to get 2x equals 28. And finally, divide both sides by 2 to get x equals 14. Or so we think. Because the index was even, we need to check the answer to make sure it's correct. So going back to the original problem, before we did any squaring, that would be 2x, which we claim was 14, minus 3. We hope the answer's 5. Well, 2 times 14 is 28 minus 3, which we hope is still 5. And 28 minus 3 is 25, which we hope is still 5. And in fact, the square root of 25 is 5. So yes, our answer, x equals 14, is correct. Let's try another one. How about the square root of 5x plus 2 minus the square root of 3x minus 7 equals 0. This time we cannot just square both sides, because before we're allowed to square, we have to get one of the radicals alone by itself. It doesn't matter which one we solve for. Let's solve for the first one, just because it's already positive. Getting rid of the second one, we add the square root of 3x minus 7 to both sides. And that's going to give us the square root of 5x plus 2 equals the square root of 3x minus 7. And the way we get rid of square roots is we square both sides, because square and square root are inverses. Leaving behind 5x plus 2 equals 3x minus 7. Get the variable on one side by subtracting 3x. Get the numbers on one side by subtracting 2. And we're left with 2x equals negative 9. Finally, divide by 2 to find out that x is equal to negative 9 halves. Or so we think. We need to go back and check it in the original problem. The original problem was the square root of 5x, which we claim is negative 9 halves, plus 2, minus the square root of 3x, which we claim is negative 9 halves, minus 7. Hopefully that equals 0. Simplifying then, 5 times negative 9 gives us the square root of negative 45 over 2 plus 2 minus the square root of negative 3 times 9 is 27 over 2 minus 7. Getting common denominators of 2 under the radicals, negative 45 over 2 plus 4 over 2 minus the square root of negative 27 over 2 minus 14 over 2. And then we get the square root of negative 45 plus 4 is negative 41 over 2 minus the square root of negative 41 over 2. But we have a problem. Remember, we cannot take the square roots of negative numbers. This problem's not going to work out at all for us because we can't take the square root of negative numbers. This is a non-real result. We're going to cross off this solution altogether, at least until we talk about non-real answers. But for now, we're going to say, gee, that didn't work out. We can't take the square root of a negative. No solution there. How about this problem? X equals the square root of 7x plus 51 minus 3. In this problem, again, before we get rid of the radical, we need to get the radical alone by getting rid of the other stuff. So we're going to add 3 to both sides, giving us x plus 3 equals the square root of 7x plus 51. Now we can get rid of the square root by squaring both sides. Squaring gets rid of the square root, and we're left with 7x plus 51. Be careful squaring the left side. The wrong answer is x squared plus 9. That was the rule that we went over yesterday. We need to FOIL this out. We square the first, x squared, and then x times 3 is 3x. 3 times x is 3x. 3 and 3 gives us 6x in the middle, plus 3 times 3 is 9. We can solve this equation because there's an x squared and an x. We need to set it equal to 0 and either factor or use the quadratic formula. So we'll subtract 7x and subtract 51. When we do, we get x squared minus x minus 42 equals 0. And that one does factor nicely. That's x minus 7, x plus 6 equals 0. So when we set each factor equal to 0, x minus 7 equals 0, x plus 6 equals 0, we get x equals 7 or negative 6. or so we think. We need to check these answers back in the original problem. So first checking the 7. 7 hopefully equals the square root of 7 times 7 plus 51 minus 3. So we're still hoping the square root of 7 times 7 is 49 plus 51 minus 3. Still hoping the square root of 49 plus 51 is 100 minus 3. Still hoping the square root of 100 is 10 minus 3, and sure enough, we get the same thing on both sides. Our answer of 7 is correct. What about the negative 6, though? Turns out that with two answers, you could have one that works, two that works, or neither that work. So we do have to check this all the way down. So we'll go back and check again, this time with the negative 6. X is negative 6 equals the square root of 7x, or 7 times negative 6, plus 51 minus 3. 7 times 6 is 42, negative, plus 51 minus 3. Still hoping. We don't know this is equal. Negative 6 we hope is equal to negative 42 plus 51 is 9 minus 3. Still hoping the square root of 9 is 3 minus 3. But wait, 3 minus 3 is 0. This one did not work, so we have to throw out the negative 6, because negative 6 is not equal to 0. With radicals, we have to be very careful of those extraneous solutions that can get in the way. So the only answer that worked here, x equals 7. Let's try 1 equals the square root of negative 5 minus 3x minus x. Similar to last time, we need to get the radical alone before we take care of it, which means we need to get rid of the minus x by adding x to both sides. That gives us x plus 1 equals the square root of negative 5 minus 3x. Again, now that the radical is alone, we can solve by squaring both sides. Squaring gets rid of square root, leaving behind negative 5 minus 3x. And on the other side, x squared, 1x, and another x is 2 x's, plus 1 squared is 1. Again, we're going to solve by getting the equation equal to 0, adding 5 to both sides and adding 3x to both sides. This gives us x squared plus 5x plus 6 equals 0. And that one factors quite nicely. But if you ever have problems with the factoring, don't hesitate to use the quadratic formula. This is x plus 2, x plus 3. And so when we set those equal to 0, x plus 2 equals 0, and x plus 3 equals 0, we're left with x equals negative 2 and negative 3 for our possible solutions. We don't know their solutions because we still have to check our work in the original problem. So we hope that 1 is equal to the square root of negative 5 minus 3 times, the first answer was negative 2, minus x, which we're saying is negative 2. So we hope the square root of negative 5, negative 3 times negative 2 is positive 6, minus the negative 2. And actually, I'm going to say add the opposite. We're going to make that plus 2. So we hope the square root of negative 5 plus 6 is 1, plus 2 equals 1. But you can see it coming now. The square root of 1 is 1 plus 2. 1 is not equal to 3. The answer of negative 2 does not work because when we plug it into the original equation, we find it was an extraneous solution. Let's try plugging the negative 3 in then. So 1 we hope is equal to the square root of negative 5 minus 3x, which is negative 3, minus x, which is negative 3. Again, I'm going to add the opposite on the right side to make it plus 3. So we hope 1 is equal to the square root of negative 5, and negative 3 times 3 is positive 9, plus 3. So we hope the square root of negative 5 plus 9, or 4, plus 3 equals 1. But again, you can see it coming. 2 plus 3 certainly is not equal to 1. It is 5. So the negative 3 is thrown out as well. Turns out this problem also has no solution. Let's try one last problem to really get our brain thinking about how to work with these radicals. We're going to solve the square root of 4y plus 1 minus the square root of y minus 2 equals 3. Similar to the last problems we solved, we need to get one radical alone before we square both sides. So let's get the radical on the left alone, just because it's already positive. We're going to add the square root of y minus 2 to both sides. And this leaves us with the square root of 4y plus 1 equals 3 plus the square root of y minus 2. And now that that radical is alone, we can get rid of it by squaring both sides. Squaring a radical, we're left with 4y plus 1. On the right side, be careful we don't just say 9 plus y minus 2. This is a binomial with two parts to it, just like 3 plus x. This is 3 plus square root of y minus 2. The 3 squared is a 9. Then we multiply them together, giving us 3 square roots and 3 square roots, or a total of 6 square roots of y minus 2. Plus, when we square the last term, the square root goes away, leaving behind y minus 2. Let's combine the like terms to make this a little cleaner. So we have 4y plus 1 equals 9 minus 2 is 7. I'm also going to put the y next, plus y plus 6 square root of y minus 2. This might as well have been a problem that we solved earlier. Now we have a single square root that we need to get alone so that we can solve it. So we go back to what we did before. Subtract 7 and subtract y, getting the radical alone. We have 3y minus 6 equals 6 square roots of y minus 2. Now, because the 6 is multiplied by the radical, it's going to be okay to square at this point. So that's what I'm going to do, is I'm going to square both sides. The square is going to have to go on both parts, though. So we have to square the 6 to get 36, and we have to square the radical, leaving behind the inside stuff, the y minus 2. On the other side, we square in much the same way we always have. 3y squared is 9y squared. Multiplying, we have negative 18y, and negative 18y is negative 36y, plus 6 squared is 36. We've now reduced this down to something we've been solving for a long time now. Distribute the 36 through, we have 9y squared minus 36y plus 36 equals 36y minus 72. Then we get the variables on one side by subtracting 36y. Actually, we're going to make it equal to 0 because we want a factor. Add 72, and we get 9y squared minus 72y plus 108 equals 0. Now we can factor. Remember, with factoring, we always look for the GCF first, and this has a GCF of 9, which is really convenient, giving us y squared minus 8y plus 12 equals 0. And then continuing to factor, that's y minus 6, y minus 2 equals 0. And we set each factor equal to 0. The 9 doesn't have a variable in it. We don't care about that. Y minus 6 equals 0, y minus 2 equals 0, giving us two possible solutions of 6 and 2. Possible solutions, though, because we have to plug them back into the original problem to make sure they work. Let's start with the 6. Plugging 6 into the original problem, we get the square root of 4 times 6 minus 1, minus the square root of 6 minus 2, which we hope is equal to 3. Oh, I'm sorry, it's plus 1 inside the first radical. 4 times 6 is 24 plus 1, minus the square root of 6 minus 2, which we hope is equal to 3. 24 plus 1 is 25. 6 minus 2 is 4. We hope this is going to be equal to 3. And sure enough, the square root of 25 is 5. The square root of 4 is 2. It does equal 3. So our first answer of 6 is a good answer. We still have to test the 2, because sometimes both work, sometimes one works, and sometimes neither of them work. So this time testing the 2, we have the square root of 4 times 2 plus 1, minus the square root of 2 minus 2, we hope is equal to 3. Well, 4 times 2 is 8 plus 1, minus the square root of 2 minus 2 is 0. We hope this is equal to 3. 8 plus 1 is 9. Square root of 0 is 0. That's really boring. And you can see the square root of 9 is 3. It does, in fact, equal 3. That's a true statement. The answer of 2 also works. And so for this problem, we had 2 solutions. This video covered a lot of content. What radicals are, how to simplify radicals, how to multiply radicals, how to divide radicals or rationalize denominators. We talked about how to add and subtract radicals, and ultimately how to solve equations that have radicals in them. Take a look at the homework assignment in the book. We will see you in class.